to our second, I think, seminar this quarter in physical sciences, machine learning Nexus. So today, a little unusually, we have one of our most junior speakers. Jessica Howard is still a PhD graduate student in particle physics in the physics department here at UCI. She is a National Science Foundation Graduate Research Fellow, and she's also been a MAPS Honorary Fellow. That's the Machine Learning and Physical Sciences program run out of computer science. She graduated from UC Davis in 2017 with a BS in physics and a minor in math. So her field is particle physics, which hasn't been greatly represented in this series so far. And of course, it focuses on studying the interactions between subatomic particles. Now, what Jessica has been doing is using machine learning to try to help solve some outstanding particle physics problems. So in particular, applying machine learning tools to data that comes out of particle collision experiments and trying to improve event classification. So she's also interested in broadening these applications of machine learning to more general problems in theoretical and phenomenological particle physics. And with that, take it away, Jessica.
Thank you. Thank you so much for the introduction, and thank you for having me. I'm really excited to talk to you all today about this work. So this work is focused on trying to make faster data-driven particle physics simulations using machine learning. But since this is a fairly, since this audience spans a lot of different fields, I'm going to try to focus a little bit more on kind of the high-level motivations for what we were trying to do and the machine learning method, and a little bit less on the particle physics specifics. But if anyone has questions about those as well, I'm happy to answer them. So let's dive in and get started. So the first thing that I want to start off with is really motivating simulations and why we need them in particle physics. So I guess to broadly state the goal of physical sciences, we're really trying to build models of different physical phenomena and then try to validate those models with experiments. And the reason we're doing this is to use these models to make predictions or just learn a little bit more about how our universe works. Simulations are often used in this pursuit, and the reason why is they let us translate these theoretical models into a form that we can then compare with experimental data. And this lets us then answer the question we really care about, which is how valid are these models? But you might be wondering, why do we need simulations? Why are they necessary? And the reason is that they're necessary when it's difficult to translate your theoretical model predictions into a form that you can directly compare with your experimental data. And to put this another way, simulations are really crucial when your theoretical model can't predict directly measurable quantities. It can only predict indirectly measurable quantities. And so to kind of expand on what I mean by this, I prepared a little kind of high-level analogy. So imagine you have a theoretical model that describes the wine produced by vineyards. This model has any number of parameters, including possibly the location of your vineyard. So you want to test this model, and you're given a glass of wine. The most direct way to test your model would be to the most direct way to figure out where the vineyard was located that produced the wine in your cup would be to just read the label on the bottle. This would be a direct measurement. You can find exactly the location of the vineyard that produced the wine that you're drinking. But say you didn't have this. Say the label on the bottle was incomprehensible, or you didn't have the bottle to begin with. You might think that you're out of luck, but there are ways that you could still get at this information in order to test your model. So imagine that you're fairly skilled at discerning the flavors of the wine. You might be able, from your experience, to then guess the location of the vineyards from the flavor of the wine that's in your glass. You could say whether it came from France or Napa Valley, for instance. But this process is very imprecise and prone to errors. And so it's very unlikely that you would be able to guess the precise location of the vineyard. What's more likely is that you would have a distribution of guesses with a most likely value, where you think the wine actually came from. You can then compare this distribution of your guesses to the prediction from your theoretical model. And this distribution is your experimental data. So the process is we've taken these indirect measurements and reconstructed them into a form that we can then directly compare with our model's predictions. In particle physics, we don't have vineyards and we don't have wine. What we have are particle interactions, theoretical models about the particle interactions, and the particles that are produced, their properties. And so these particles, which are labeled U and D bar here, unfortunately, they're very elusive. We can't see them with our detectors directly. So any kind of direct measurement is unavailable to us. Instead, what happens is these particles decay and turn into thousands of other particles that then hit our detector. And so we're left to reconstruct what happened from all of these indirect measurements into a form that we can compare with our theoretical model. Namely, we construct them into parameters of our theory, like the masses of the particles. And this is why we really need simulations, is because particle physics is full of these indirect measurements. So now that I've motivated why particle physics needs simulations, I'll tell you what's wrong with them. And the biggest problem with particle physics simulations is that they are incredibly computationally costly. And this is really limiting our ability to discover new physics and perform analyses. And this is only going to get worse with the future experiments that are planned. And this computational cost is largely due to the fact that there are a lot of intermediate steps in these simulations. So particle physics simulations can really be split into four main stages. And these stages are meant to try to mimic what happens in reality. The first stage deals with calculations in our theoretical model space. And so this is very well described with the mathematical language of our models. So these the computations at this level are well understood and also fairly computationally efficient. So that space isn't the problem. What's the problem is the last three stages that deal with indirect measurements and reconstructing them into experimental data. These stages are much less theoretically well described, and they're also much more computationally costly. And so this is where the problems of these slow simulations really live. Now, I'll just note, kind of in analogy with the wine example that I gave, the purpose of these simulations is to really try to match your information in your theoretical model to your information in your experimental data. So these spaces should be very similar. They often have similar dimensions and similar properties. And in fact, if you think about it, if our detection and reconstruction process were perfect, so if we were perfect at guessing the location from the flavor of the wine, these two spaces, your theoretical model and your experimental data, should be exactly identical. So what you realize is this experimental data is a deformation of your theory space information due to detector imperfections and inefficiencies. Current simulations try to get from one end to the other by traversing this really high dimensional space, but this causes them to be really computationally costly. So what we wanted to do in this work, and what kind of inspired us with this kind of looking at the endpoints, is to just skip from one end to the other using machine learning. So specifically, we were trying to answer the question of, can we predict experimental data given information from our theoretical models and do this in a completely data-driven way? So the hope is that machine learning can help us make faster particle simulations. And we're not the only ones who are trying to jump on this wagon. There are a lot of others trying to tackle this problem with machine learning. But previous solutions really focus on trying to substitute out the slowest parts of this current simulation chain, or multiplying the data sets that you get at the end. So they're trying to augment current simulations. Whereas what we were trying to do is something a little more ambitious, which is to try to replace current simulations with a machine learned method. And so in this talk, I'll be talking about the foundations of how to go about this. The method is fast. It's completely data driven. So it can be trained using real data from something called control regions in particle physics, which are just the regions of data space where we know what's going on in the underlying theory. But specifically, we're independent of current simulations. We don't need those to train this model. This model also provides the ability to include physics-motivated constraints. And the final mappings that you get at the end, the final simulation, is both easy to inspect and also interpret. So we call this method optimal transport-based unfolding in simulation, or OTUS for short. And it turns out that OTUS is a genus of owls. So we got a cute mascot out of this as well. Okay, before I dive in to the details of the method, I want to very clearly set up the mathematical notation that I'll be using through this. This method relies a lot on statistics and probability theory, so I just want to make sure that we're all on the same page. So over on our theoretical model side, our theoretical models belong to a theoretical model space, which we'll be referring to as Z in this talk. And the properties of the particles that belong in this space follow some probability distribution, so P of Z. Analogously, our experimental data belongs to an experimental data space called X and follows a probability distribution P of X. Now, the task we're trying to accomplish is to map from theoretical models to experimental data. And this can be expressed as just mapping from Z to X. And what this is in probability terms, it will follow a conditional probability distribution. So P of X given Z. Okay. And I'll note here that kind of by definition, the experimental and the theoretical data spaces are related, but they are not necessarily completely analogous. For example, they can have different dimensions, and this really gets at what kind of detection deficiencies do you have? Do you miss a particle entirely? That's the sort of thing that would contribute to these spaces being different. Okay, so to very clearly define in machine learning terms what we're after. So what do we want? We want a conditional mapping from our theoretical models to our experimental data. We want this mapping to be stochastic. This is in part to account for the quantum mechanical randomness of particle interactions. And we want the option to train on real data and not data produced by a current simulation. And specifically what this means is that we don't have any training pairs. We're trying to learn this transformation, but we don't know the specific pairs of the endpoints. Translating this into machine learning terms, what we want is a conditional, generative, stochastic machine learning architecture that can be trained with unsupervised learning. And so I'll summarize that as just 3 short rules, and we'll try to address those with whatever method we choose. And so I will save you the details, but after searching high and low, we were able to find a machine learning method that was able to satisfy all of these rules. And this method is called sliced Wasserstein autoencoders. And just to give the more technical, machine learning technical people in the audience kind of a preview of where I'm going with this and why this meets all of these rules, I want to talk about the main differences between this sliced Wasserstein autoencoder method and a typical probabilistic autoencoder like a VAE. So firstly, the loss function is entirely based in optimal transport theory. So it's a different formulation of this kind of autoencoder loss. One important feature is that it uses the sliced Wasserstein distance as its latent space loss. And I'll talk more about the details of what this looks like. But this optimal transport theory framing really provides a lot of mathematical advantages that I'll get into later. One other advantage is that the latent space can have any sampleable prior. This is not something that is typically possible, or it's very difficult with traditional VAEs. And so this is great for us because we can identify this latent space prior with the model, with the theoretical model prior. And so we're then able to get this conditional mapping between our 2 spaces. So that satisfies rule number 1. Rule number 2 is that the entire loss function here is actually likelihood free. And so what this means is that our networks can take noise as an input, so they can be stochastic, just like we want them. And I already mentioned this is an unsupervised method. So we've satisfied all of our constraints for this problem, but there's actually several bonuses here, but one in particular is that we get a reverse mapping for free. So not only can we map from theories to experimental data, we can map in the reverse direction. And particle physicists refer to this as an unfolding mapping. Okay, so to show exactly what this network looks like. So like probabilistic autoencoders, it has 2 networks. There is an encoding network and a decoding network. And what we're trying to do is we're mapping between the 2 spaces. So we're going to identify the encoding network will act as our unfolding model, and the decoding network will act as our simulation model. So we're going to be mapping from our experimental data space to our theoretical model space, and then back into our experimental data space. So to follow a given sample kind of through this chain, we take a sample of experimental data from our experimental data distribution. It's then encoded into our theoretical model space, producing this Z tilde. This is then compared distribution-wise with our theoretical model space prior. And this is done via the sliced Wasserstein distance. And I'll just note here that this P of E given, or P of E, PE of Z is the marginalized encoding distribution with the mathematical definition there, and this will be important later. So the Z tilde is then fed back through the decoder into our experimental data space, producing this X tilde. This X tilde is then compared with the initial input pairwise via this data space loss function. And in this work, we chose the cost function to just be an L2. So a Euclidean distance between the two data points. Okay, these two losses are then combined to give the overall SWAE loss, and they're combined with a relative hyperparameter weighting between them called lambda. Okay. Focusing in on the loss function, I mentioned that the latent space has this sliced Wasserstein distance, but I haven't actually told you what the sliced Wasserstein distance is. So I'll go through that now. But before you can understand the sliced Wasserstein distance, you have to understand what it's trying to approximate, which is the Wasserstein distance. So the Wasserstein distance is very important in optimal transport theory, and it measures the cost to morph one probability distribution into another via the optimal transport plan. And this sounds very abstract, but the best way to think about this is to imagine being given a pile of dirt and tasked with moving that pile some distance and reshaping it to have a different form. The sliced Wasserstein distance is the cost of performing that action, assuming that you knew the optimal way to move the dirt from one location to another. Now, the Wasserstein distance is great. It has a lot of great mathematical properties, but unfortunately, practically speaking, it's very difficult to calculate. It's really only tractable when you have one-dimensional probability distributions. And the reason for this is this note about you need to know the optimal transport plan. So there's an inherent optimization problem inside of calculating this distance. And this becomes extremely intractable the higher dimensional probability distribution you go. But in the one-dimensional case, it's actually analytically known. The transport plan is known, and so you can very easily calculate this Wasserstein distance. And what it is exactly is just related to the difference between the inverse cumulative distribution functions of your probability distributions. And just as a side note here, I'll note that this can be approximated from finite samples, in which case your CDF becomes an empirical distribution function. And this will be important in a couple of slides. Okay, so now that we know what the Wasserstein distance is and why it can be problematic, let's see how the sliced Wasserstein distance tries to fix this. So the sliced Wasserstein distance tries to approximate the Wasserstein distance. And specifically how it does this is it takes your high dimensional probability distributions, projects them onto a series of one-dimensional slices, and then along those slices, it calculates the tractable one-dimensional Wasserstein distance. And then after all of this is done, it averages the result over all of these slices. And I'll save the details, but it can be mathematically proven that in the limit of infinite slices, the slice Wasserstein distance is exactly the Wasserstein distance. But it is an effective approximation for finite number of slices as well. So, so that's useful for us. Okay, so coming back to the loss function, I told you what the slice Wasserstein distance is in this fairly abstract form, but for finite samples, it becomes this tractable estimate that we can then use in a machine learning model. So specifically, the terms stay the same, but it has these sums here. And so I'll note that the data space loss function, because we chose our cost function to just be an L2, this data space loss is just mean squared error between x and x tilde. And then the latent space loss, I'll just comment here that there are two hyperparameters. There's the number of finite samples that you've used to approximate your probability distribution. And so you can think about this as being your batch size during training. And then there's the number of random slices as well. So these are two hyperparameters that you need to account for during training. Okay, I'll pause here for a second before talking a little bit about the mathematical benefits. So are there any questions?
May I ask a question?
Mm-hmm.
So does this slicing method, you said in the limit of infinite slices, is it a solution to this optimal transport problem? Like an acceptable solution as far as the mathematicians are concerned?
Yes, it provides a bound on the Wasserstein distance, essentially. So it's perfectly acceptable to use during training.
Okay, so with a finite number of slices, you get a bound.
Yes, exactly.
On the infinite slices thing. Okay, thank you.
Mm-hmm.
And people can either speak their questions or put them in the chat. Okay, so maybe we keep going.
Okay.
Everybody's followed everything.
Cool. Okay. So just as a short aside, I want to talk a little bit about the mathematical benefits that I promised several slides back with using this method. So number one benefit is that all of the components of the loss function are actually true distance metrics. They satisfy all of the axioms of a distance. And so practically, this leads to several advantages. So one is that they're always well-defined during training. You don't have any sort of problematic divergences, which can happen in both adversarial and also traditional like VAE methods. There are both cases where those loss functions can be problematic, but this case does not have those. This also makes it easy to add on additional physically motivated constraints to your loss. So you just are able to tack them on sort of at the end as additional loss terms. And so this can be very useful when you're trying to make physical mappings. So that's another benefit. The other kind of major class of benefits is that the different parts of your latent space are allowed to be disjoint and stay disjoint during training. And this is somewhat of a subtle point, so I want to expand on it a little bit more. But this, the summary of it is that this is a very useful property when you're trying to identify your latent space with the space of theoretical models. So in particular, this idea of your theoretical or your latent space not remaining disjoint is a problem with traditional probabilistic autoencoders. It's actually a form of information collapse between the two spaces. So I'll say both mathematically what I mean, and then also kind of visually represent what's happening, what this sort of loss is encouraging. But the problem really stems from the latent space loss function in traditional VAEs, because it compares your encoding distribution with the latent space prior. And so what this encourages is that every data point in your experimental data space is then mapped to your entire theory space prior. And this is no good if you want some kind of conditionality of X given Z, or Z given X, because your data point could be mapped to an entirely different part of the theoretical data space, and that might not be physical. Fortunately, this can be fixed, and the solution is to actually match distributions instead. And this was a problem that was solved by a precursor paper to the method that the slice-Wasserstein autoencoder method that we're using. But the solution is to match your marginalized encoding distribution with your theoretical model space prior. And so how this differs is that every point in your data space is now mapped to a sub-distribution in your theoretical model space. And then these sub-distributions conspire to eventually build your entire theoretical model prior. So you've been able to restore this conditionality of the two spaces on one another. And this is very useful when you're trying to make sure that this simulation mapping is physical. Okay, so that was a lot on the method. So now I'm going to go through the test cases from particle physics that we investigated. So I'll go through this at kind of a high level, but if anyone has more specific questions, I'm happy to answer them as well. So we tried two different test cases, and these are common particle physics examples of data that is used to tune simulations. And so we wanted to use those in our case, and so we picked an easy case and a hard case. Essentially, the theoretical model space comprises some number of particles. Each particle is described by 4 numbers. They're 4 momenta. And so in test case number 1, this theoretical data space is 8 dimensions. In test case number 2, it's 24, because there's 2 and 6 particles respectively. Similarly, the data space are the respective objects that you would actually detect detect and reconstruct. And I'll just note that here we've kind of restricted the scenarios such that both the Z and X spaces are the same dimensions, but this does not have to be true in general. It just is true for these test cases. Okay. So jumping straight to the results. These are the results of the simulation mapping. So mapping from your theoretical space to your experimental data. And we're trying to match properties at a distribution level. And so these are just a few different samples of the properties from these large dimensional spaces. Black are the curves that we are trying to match. So these are the truth distributions given by the simulator that we use to produce our data. And you can see that in both cases, we do quite well at matching these different distributions, although in the easier case, so the Z-boson decay on the left, we do quite a bit better at matching than in the harder TT bar case. Similarly, we can look at the results for the unfolding mapping. So now we're going from experimental data to theoretical models. Here we can see again that the matching is very good in both cases, although slightly bit better in the left side case, which is the easier test case. But we weren't just interested in how well it did at the distributions we were asking it to match. We were also curious what it was able to pick up on implicitly in the relationships of these data. So obviously we want our simulation mapping, our final mapping to be physical. And we can't always account for all of the physical relationships that will exist in our data set, known or unknown. So we were very curious about whether it was doing things that are sensible, physically sensible, as opposed to just matching the distributions. And so in order to test this, we took the properties whose distributions we were trying to measure, and we combined them in ways that physically make sense and should be valid and give sensible answers. And we did that for both the truth data and also the predicted results. And what we can see is that in both cases, while not perfect, it is able to pick up on these implicit sorts of relations. So the left-hand side case, this is the mass of the Z-boson, which is obtained from combining the information from the electron and the positron in a very particular way. And you can see that here it's actually able to match these distributions right here. And we did not tell it to learn this distribution. This is something it was able to pick up on it just implicitly from the data. In the harder TT bar case, it did slightly worse, but this problem had a lot of challenges with it that we tried to tackle, but really should have a more robust data description. So it's not surprising that it wasn't able to do as well as the easier case, although it did do quite impressively and is actually making a lot of sense in what it's doing. So that's really exciting. Another way to kind of probe what did our network learn, are these mappings sensible, is to really just crack them open and look at exactly what they are doing. And so one way to visualize this is with what we call transport plans. So this is really looking at how probability mass from your theoretical model space is transported into your experimental data space. And so the top distribution is your distribution in your theoretical model space. The right distribution is the distribution in your data space. And the colors on each bin correspond to where that amount of probability mass was distributed in your data space. And this black and white distribution in the middle is the joint distribution between these two spaces. So what we can see by these is actually quite promising. It's not doing anything that's concerning or unphysical. For example, it's not mapping information that's on the tails all the way to the peak. It's kind of keeping this idea of similar information in Z should roughly stay in the same place, which is exactly what we would hope for. So this is extremely promising on its own. But since this is a proof of principle scenario, we can cheat a little bit and look at the answer of what exactly these mappings should look like. Specifically, we can make these plots for our simulated data. And we wouldn't be able to do this if we were actually training this method on real data, but because this is a proof of principle, we can cheat a little bit and look. And so what we see is actually pretty impressive in that it's been able to kind of pick up on this transportation, and the transportation that it chooses actually looks pretty physical. And so that's really exciting. So not only have we been able to match the distributions, which is what we were trying to learn, but we've also managed to pick up on the physical nature of this transformation just implicitly from the data. So just to summarize what we concluded from these test cases. The performance was quite impressive and also physically plausible, which is good. It was able to successfully learn or approximate implicit relationships in the data, so relationships that we did not tell it to learn, that it would only have been able to pick up on from the data. It still needs some amount of improvement, but there is a lot of evidence that we found that this improvement will come with more robust framing of the data. The way that we described our particles is with 4 numbers, but there are a lot of other features of particles, for example, charge or spin or type, that we excluded in this data set. And so there are a lot of rules that go along with those that would help the network make a more physical mapping. So, so that's an area of future work. To talk in a little bit more detail, so we really need a more robust data description that is capable of having both continuous and categorical properties, as well as the structure between the different particles. And there are a lot of methods that are promising in order to be able to do this. We just didn't pursue them for this proof of principle work. We also need to be able to handle variable types and numbers in particles, of particles in both your theoretical and your experimental data, because more than one configuration of particles in your theory space can map to the same experimental signature and vice versa. And so you really need to be able to robustly handle those different states in both cases. And particles of a certain type will be there and then not between samples. And so you need to be able to handle that in your machine learning description. And then lastly, assuming we can make all of this work, the last kind of step towards building this to a full simulation would be to interpolate between these control regions. So I mentioned before that control regions are areas of the data where we know what's going on in the underlying theory. And so these can be used to tune your simulation. But these control regions can't cover all possible corners of your spaces. And so you need to be able to use the spaces that you can to train your network, and then it needs to be able to do something sensible when it's moving between these regions. And this problem, we think, is not insurmountable, and in fact, it's actually the same problem that faces current simulators. So we're pretty confident that this won't count this machine learning method out when we get to that point. And then quickly before I end, how am I doing on time?
You're doing fine. We're at 2:47, so you got about 5 minutes to wrap up, and then we'll do questions.
Okay, cool. So, so just a slide, since we're all from a lot of different fields, I wanted to talk about some of the different choices you can make in tweaking this model, depending on the problem that you're trying to solve. So theoretically, this model can be applied to any problem that is attempting to learn a transformation between arbitrary probability distributions. Some useful features that you could be able to tweak depending on your given problem. These mappings that you learn can be deterministic or stochastic. The spaces can have the same or different dimensions. The distributions can have a known form or only be known via samples. Although I will note that in the case where you're using the finite sample estimate of the sliced Wasserstein distance, you do need a lot of samples in order to be able to accurately estimate the empirical distribution functions and really, really get the error down on the distribution matching. A few other options. You can actually train only the decoder or only the encoder using this sliced Wasserstein distance as the loss. And so you can think about this as a GAN sort of alternative because you're learning a mapping, but it's still in an unsupervised way. Although if you tackle it from this side, you will likely need a lot of additional mapping constraints to make sure that the mapping is physical. And then another thing you can do is turn this into a semi-supervised setup. And here in this work, we were really focused on being completely unsupervised, but there is a strategy to use a small amount of pairs to help constrain the mapping with an alternate approximation of the Wasserstein distance. And the way that this approximation works is that assuming you know some set of pairs, Z and X, you've effectively fixed your transportation path. So it might not be the optimal path, but it is a path. And so it will be an upper bound on your Wasserstein distance. So for the set of samples where you know the pairs, you can use that. And for the set of samples where you don't, you use the sliced Wasserstein distance as normal. Okay, so just to conclude, this is a new approach to doing fast simulation in particle physics. It's the first step towards a completely data-driven simulator using machine learning. And as a bonus, not only do you get a simulation mapping, but you also get an unfolding mapping. So you can go in both directions at the same time. This approach has a lot of mathematical advantages. And the performance on these simple test cases is quite promising, although there is some amount of future work to do to scale it to being able to handle a full particle physics simulation. So that's all I have. If anyone has any questions, I'm happy to answer them.
Okay, well, thank you very much. So now we can have some questions. I don't know if you want to stop sharing, or I guess we're okay. Yeah. So you can either put questions in the chat or just directly ask, turn on your microphone and ask some questions.
Just a quick one. When you have different dimensions in the space, do you have to do any padding?
Yes, you or the padding would inadvertently be done by the networks. So it's, we just used feed forward networks, so it would just be changing the output dimension side, but in effect, it would be some sort of informed padding. You could interpret it that way.
And when he achieves the latent space, they have all the same dimension at that point, right? Or
so when you're comparing latent space to latent space, it has the same dimensions, and same with experimental space to experimental space. But the theory space, which is the latent space, and the experimental space could have different dimensions.
thank you.
Can you say anything about sort of the amount of data needed? I guess you showed us some nice results in these test cases, but did you sort of go back and remove data and see sort of how much you need to get results reasonably good?
Yeah, so we didn't do any sort of intense study about like what's the minimal data set size, but we, I'm blanking on the exact numbers, but I think in total between the data space, or sorry, between the training, testing, and validation sets, since we had 3 sets, I think we had about 400,000 data points total. And so we split those up, but I forget the exact way that we split them.
Sure. So that was 400,000 for the cases that you were showing us?
Yeah, for each case, respectively. Yeah.
Right. And then I believe you folks in particle physics have these things called conservation laws, right?
Mm-hmm.
But you were saying, so if there was an a conservation law, let's say first that you knew about,
mm-hmm.
you were sort of saying you can add in like penalty functions into the loss, for example, to enforce them, right?
Yes. Yeah, so there were 2 kinds of constraints that we actually did use in these particle physics examples to take advantage of exactly what you were alluding to. But I didn't have time to go into them in detail. But essentially so for example, one constraint that we did penalize it for was in the easier test case. So the theoretical model space and the data space actually had the same particles and the same dimensions, but these 2 particles were an electron and a positron, and they look almost identical except for their charge. But like I mentioned, we didn't put in discrete properties like charge, and so we kind of had to backdoor a constraint in to penalize it so that it wouldn't map a positron to an electron or an electron to positron. And so we were able to do that successfully, but it would be far better to be able to naturally express those sorts of categorical and discrete properties with the particles. And so there's some methods that would be able to do that. We just didn't look into them for this particular work.
Right. So yeah, so that's like discrete thing, and so it's trickier to put in as a,
mm-hmm.
a loss function, right? And then so you mentioned like so they have solutions, simple solutions for the transport problem in 1 dimension, right?
Mm-hmm.
We know it. So did you think about sort of running this on a sort of 1-dimensional example where you sort of know everything about what's going on?
We did not. We didn't do that because in order for this to really be practically useful for particle physics, the dimensions are on the order of 10. So yeah, so we didn't look into that just because of the problem we were trying to solve, but it would be interesting.
Well, yeah, more as a almost pedagogical example, right? To to see sort of exactly what it is doing. It can be very useful, and also for illustrating.
Yeah, we did do a test a test toy problem in a two-dimensional case, so it was much more
Yes.
visually interpretable, but yeah, not the one-dimensional case.
And is that included in the paper, the two-dimensional?
No, we didn't have space to include it, but.
Right, or maybe the energy to include it. Yeah. And then I gotta ask, so for applications to other areas, right? So one that immediately strikes me is we have this problem in sort of chemistry and materials where we have the sort of quantum solvers for the electrons, and we have ions, right? And we're sort of doing a simulation where everybody's moving around, but we have to keep solving for the quantum mechanics of the electrons, which is very, very expensive. What we would like to have are these classical force fields to run just Newton's laws on the ions in these effective force fields, which then are almost infinitely faster to run. But then finding the force field and finding an accurate enough one and so forth is problematic, and a huge number of people are working on machine learning methods for producing force fields with considerable success these days. So it seems like this OTUS method might apply to that problem.
Yeah, I think so. Based on that description, it does sound promising, and I'd be happy to talk about it in more detail also.
Yes, because that would be a fantastic application, and also there's like sort of huge numbers of people and resources already invested in this, and they're all doing sort of significantly different things, and nothing quite as sophisticated, I think, as yours. Okay. Do we have any questions from the rest?
None in the chat.
I guess I could ask a question. I'm not too experienced in either of these fields. I'm sort of beginner in both, actually. So I just have sort of a conceptual question about how this might be used to abstract to maybe like a particle you haven't seen before. Like, so, you know, you're using, this is data driven with real data. So you can, you know, find some correlations between particles and their interactions. So if you wanted to say, I mean, the purpose of this, you know, you said was to not be simulation data driven, but could you do some, I guess, what's it called? Modified learning, like what's it called? Sorry, I can't think of the term for when you add data on a pre-trained model.
Transfer learning.
Transfer learning, yeah, like transfer learning. So you have a mathematically driven simulation that shows you should get like a Higgs boson, and you have this real data where you can't find the Higgs boson. I'm wondering if maybe that method could be used, or if your current method could be used to find sort of things you haven't seen before.
Yeah, okay. Yeah, so there's so that's actually so variational autoencoders, which are somewhat related to this method, are frequently used for anomaly detection, which I think is pretty close to what you're describing.
Okay.
What you're describing there. In terms of this method, our goal is to really allow it to give something, or I guess I'll say the anomaly detection, the way that it works is essentially once you go outside of your training region, the network produces nonsense. And so you use that production of nonsense to indicate when something has something new has entered the problem. for this method in particular, we're trying to not have that happen. So I don't think this would work too well for the anomaly detection. But what you're asking about really touches on this problem of how do you make it into an actual simulator? How do you interpolate between these different control regions to spaces of theory where you want to look for? So you can't look at the data there yet because you don't know what's there.
Yeah.
And so it's a very good question. This is actually what happens with current simulations, as well as what we would be trying to do in this case. And so there's a fair amount of you kind of pin down your model in all of your control regions and hope that it does something sensible in between. And you can, it really gets down to very delicately choosing your control regions and also building in different symmetries, conservation laws, that sort of a thing, such that it will interpolate into those unseen regions and give something that's sensible.
Okay. Yeah, it's a good answer. Thank you.
Okay. If there's no further questions. Nope. So I'd like to thank Jessica once again. Thank you very much.
Thank you. Yes.
Thank you. That was very interesting.
All right, everyone.
I was going to mention your analogies were beautifully done.
Oh, thank you. It's the first time I tried them out, so I'm glad to hear that.
I feel bad that you particle physicists don't get any wine, right?
You just don't know where it came from.
Right. Yeah.
So we hope to see you when, in 2 weeks or 3.
Who?
We have one session scheduled for May 25. That's the next one we have, but we'll probably have before that, right?
Yes, I'm working on it. Yeah.
All right.
Oh, yeah. So just Jessica. So yeah, I think we should talk.
Okay.
Quite soon about exactly that thing I was bringing up about the force fields.
Yeah, that sounds great.
I'm not sure, but I think it can be applied to that. And like I say, there's tremendous interest in doing that kind of thing. And it's like, you don't know how sophisticated the force field needs to be when you start out. And you sort of systematically go through more and more complex force fields.
Okay.
To reproduce your training data as well as you can.
I see. Okay.
So, ultimately, if you have, say, 10 nuclei, 10 atoms, then if you have 10 body forces, you can definitely reproduce everything. But, you never want to go that far. So the hope is to find something that is good enough for. Yeah. So and I, Stefan Mant and I were talking about, there's a sort of new funding opportunity from DOE.
Oh,
so
okay.
If this did happen, to be applicable to that problem, I think a lot of people will be very interested.
Yeah, it sounds.
A huge amount of stuff is already exists of what people have done. Yeah. So I mean, and I really like the way it's sort of much better mathematically formulated than a lot of stuff is just grabbed off the shelf. We ran this very, very large neural network, and we just stopped it here, and and now it's working just fine, right?
Yeah, that was the other thing I forgot to mention. But the networks that we wound up using are actually fairly small. I think they're one or two layers and like 128 nodes per layer. So, and they're just feed forward networks. So,
So really very simple. Yeah.
mm-hmm. Yeah.
And not really deep, right? I mean, some people will claim that's deep because it's more than one, but not really deep, right? So actually, one other thing I wanted to ask you about was can't you sort of, what happens if you run it through and get the data and feed it back in again?
Oh, I see. Like
round and
like
round and round and round and
round and round. Yeah, I don't know.
Is there some sort of stability analysis one can do where it shouldn't go down a rabbit hole?
It sounds somewhat similar to at least schematically to graph convolutions, because that like a graph network kind of message passes around itself many different times. And I know those have problems with like the signal getting diluted. So I would imagine that there might be issues with that.
The noise will grow, right? I think so. Hey, Daniel.
Hey,
Nice to see you.
just hanging out. If there's any, but Jessica's answering all the questions with aplomb as usual. So, I'm just hanging out in the background. Glad to hear there's some potential other applications for these ideas. We always thought this seemed like a sort of larger problem than just ours. But we don't really know enough about the problems in the other fields to know whether this would suit.
Well, the other sort of big thing is all the sort of hydrodynamics type simulations, right? I don't know enough about them to see how it might be useful there. A lot of that is kind of crossing the length scales, say training on one length scale and then being able to simulate on another.
Mm-hmm.
And it's just like a very different kind of problem. So I have a feeling it doesn't kind of translate to this kind of problem directly. But I don't know, right? I'm not an expert in that.
I think I'd want to know a little more about the different problems. I'd be able to say something a little more intelligent, but
yeah. Well, we should just arrange a time to get together. See if we can get Stefan as well. Although I'm not sure how much he would know about this a bit. But yeah, there's just to see if, just like totally naively, if the methodology, if I told you what the sort of data was and sort of how you get it and then what you're looking for, if you think it would work.
Mm-hmm.
And then it would be trivial to generate, two-dimensional data or something like that to actually run it on.
Mm-hmm.
To see, even in 2 dimensions.
Yeah. So it sounds like the problem is really trying to do like classical fit to a more robust simulation. Is that an accurate interpretation, or?
Well, it's trying to sort of generate these force fields.
Mm-hmm.
So so you needed to be distribution to distribution, right?
Mm-hmm. But you can pretty much make a distribution out of anything, more or less.
Right.
So.
Right. And in a sense, right, I mean, you sort of have limited, so people run the simulations with different levels of the quantum mechanics that can give higher and higher accuracy at higher and higher cost.
Okay.
But then they can generate sort of arbitrary configurations of the atoms, and they have various schemes for choosing these things, and then you try to sort of, within limitations, try to find these classical force fields that would reproduce that data. So so it could be like it would be a molecular dynamics type simulation, right? Can you sort of create a force field that follows the same as the quantum simulation gave you? Okay. Within certain limits of accuracy. Mm-hmm. So I tell you what, I'll look at the paper some more, right? And see if I can formulate something. Yeah. Okay. Yeah, we can also meet first and talk about it. I'm happy to do that. Right. Yeah. So yeah, not this week, but next week. Sounds great. If you're around, if you're not doing anything. Yep. Sounds good. Traveling? No. Has all the, like, how have particle physics experiments dealt with the pandemic? Has everything stopped, or all the people from the other countries not coming to? I honestly don't know. I just work on my computer. I don't know what the real experimentalists are doing. Daniel, do you know? Like how everyone's been managing with the pandemic and all at CERN? I think, can he hear us? I don't think he can hear us. Yeah, maybe.
Yeah, I have to go, unfortunately.
Yeah, he's been distracted. Okay, so let's chat some more next week. Yeah. Sounds
good. You guys did the hopping HPC 3, right? The new HPC?
Sorry. I missed the first part of your question.
When you mentioned you're using HPC, you mean HPC 3, right?
We generated the data on HPC before it made the transition, but yeah, it should work HPC or HPC 3.
Are you using that crisp storage facility from RCIC?
The final data sets are actually not terribly big, so they're just on my public directory.
Local. Okay.
Yeah, just local storage. Yeah.
All right. Thank you. Thanks again.
Yeah.
Thanks very much.
Thanks so much for having me.
That was great, and the style was fantastic. Yeah.
Okay, perfect. I'm glad.
Just include that two-dimensional example as well. All right.
Okay, sounds good. Yeah.
Okay.
Hey, Jessica.
Thank you, Jessica. Got a lot of math to research now. Nice.
Bye, everyone.
All right.
All right, y'all have a good weekend. Thank you.
Bye. Thank you. You too.